Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustion, Module 5, Combustion and Thermochemistry. So, in this module we have covered a majority of the lectures, that is thermodynamic consideration of combustion, conservation of energy for reacting systems. We also introduced adiabatic flame temperatures, Gibbs functions, entropy calculations for reacting systems. Today we will focus on some of the practical aspects, that is equilibrium products of combustion and effective energy utilizations. So, it means that by looking at the combustion products, whether which is mainly dependent on the equivalence ratio, we can say that we have properly utilized the fuel energy or not. Now, if not, what is the mechanism that can be incorporated to improve the effective energy of the fuel. So, in this lecture, that is lecture number 22, we will be touching upon the following topics like chemical equilibrium, equilibrium products of combustions, water gas equilibrium, recuperación and regeneration, flue gas recirculation. So, let me start the first segment of this lecture, that is chemical equilibrium. Prior to this, we all know that a thermodynamic system is in complete equilibrium when it is physical equilibrium, chemical equilibrium, and it is equilibrium in terms of temperature, thermal equilibrium. So, we have covered the other aspects, but when you deal with combustion process, we must know that under what circumstances the equilibrium of reaction happens. What is the criteria for deciding that the system has already achieved the equilibrium situation or not. So, this is all about we are going to study with a very important perspective or viewpoint by incorporating the laws of thermodynamics. So, we will see how we are going to use these thermodynamic laws in down the slides. If I give some introduction, and then I can say that always in high temperature combustion products, the products of combustion are not simple mixture, rather they have many complicated species that forms, and what we have dealt with so far is the stoichiometric reactions. That means, what is the exact amount of oxidizer requirement per 1 unit of fuel. So, that we have dealt that condition, we call this as a stoichiometric conditions. Now, if the reactions are not in the stoichiometric situations, and in fact it is the majority of the cases, then we will have species, combustion species, and that they will appear. And there are two types of species, one is major species, other is minor species. And this control of major and minor species is mainly governed whether the fuel is lean or rich. Now, ideally, if at all the combustion has to happen as a complete combustions, so the ideal product should be carbon dioxide, hydrogen, oxygen and nitrogen. But in most of the situations, we do not have this occurrence. We have dissociation species that are formed, which are mainly for combustion reactions are hydrogen, OH radical, OH is a hydroxyl radical, carbon monoxide, hydrogen atom, oxygen atom, nitrogen atom, NO, nitric oxide. So, these formations are very similar for hydrocarbon combustions. it is almost difficult to calculate the fraction of all these combustion products at a given temperature and pressure subjected to conservation of moles of each element present in the initial mixtures. So, there is ideal calculation is not straightforward. So, we have to rely on the experiments or observing the combustion products and taking the samples and then analyzing, we can report some of the combustion products analysis or composition analysis, and that will tell whether you have achieved the equilibrium or not. But when we want to see the theoretical viewpoint, that whether by looking at the sample of data or the experimentally measured data, we can at least predict whether these products are equilibrium products of combustion or not. But to say or to justify this fact, we have to rely on the theory of chemical equilibrium, and this chemical equilibrium has its roots with respect to second law of thermodynamics. Now, to demonstrate this fact, let us consider a fixed volume adiabatic reaction vessel with fixed mass reactants CO and O2. So, in this reactor, there is a reactor in which there are reactants like CO and O2. They are entering to in this reactor at reference pressure and temperatures, and side by side they are producing the CO2 at same pressure, reference pressure and temperature. So, as the reaction proceeds, both pressure and temperature will rise till the final equilibrium condition is reached, and the final state is solely determined by the second law of thermodynamics. And that second law of thermodynamics, what parameter we are going to find is nothing but your entropy. So, if the final temperature is not high enough, then CO2 will dissociate and the products will have components CO2, CO and O2. So, basically if it has not achieved this equilibrium conditions, the product will have some intermediate components. Now, to account this fact, let us introduce parameter alpha, and we call this as a dissociation fraction, and this can be treated as a function of adiabatic flame temperatures. Means that what is the effect of this alpha when there is a change in the adiabatic flame temperature. Why I say adiabatic flame temperature? It is because it is the theoretical thermodynamic estimates, that is the upper limit of reaction temperature. So, if you say that the reaction in a balanced form like CO plus half O2 will give CO2, now always what we look at this reaction is its final state, but what the intermediate step would have followed, that when this reactions proceeds, it has at any intermediate situations when the temperature is high, the species could have 1 minus alpha times CO2 plus alpha CO plus half O2. So, at any time instant, when you look at this chemical equation, we can find this. So, we have already assumed that to analyze this system, we have to say that ideal gas behavior for individual species is assumed, and since there is no work interactions, internal energy remains constant, space fixed volume and mass. So, what else parameter that is required is nothing but your entropy. Now, by looking at these equations, we need to calculate the mixture entropy, and we already explained that how for a ideal gas mixture we are going to calculate the mixture entropy at a given temperature and pressure, and this is nothing but your summation of their molar enthalpies, and in this case we can find out at any arbitrary instant what is the component or mole fraction of CO2 and corresponding molar enthalpy, and what is the mole fraction of CO corresponding its molar enthalpy, and same for oxygen as well. And this also can be from the data sheet or data table, one can find out the entropy of formation at reference temperature, and subsequently knowing their respective mole fractions and partial pressures, one can determine the mixture entropy. Now, if you look at these particular equations, now let us try to find out, or let us try to evolve what the first law of thermodynamics tells and what the second law of thermodynamics tells. So, if you just look at the equations, when this alpha is 0, which means it is a complete balanced equations, that means reaction has taken place, maximum heat has been released, and that is nothing that and when maximum heat is released, as per that evaluation we can do with respect to first law. Now, when alpha is 1, the mixture temperature remains unchanged because there is no heat release. So, alpha is equal to 1 means CO2 is 0, that is you have CO and half O2, when same reactants and products they remain as it is, reaction has not happened. But that is not the case. What we need to have, we need to find out the entropy. Now, what this second law imposes, that when you calculate the entropy change internal of the systems, so for a fixed internal energy, volume and mass systems, the second law imposes the conditions that this change in the entropy must be greater than or equal to 0. That means, this ds is nothing but Sp minus Sr, and this condition needs to be satisfied. And since this Gibbs function has another link with respect to enthalpy, temperature and entropy, so this gives an reverse expressions, like one can also find out the Gibbs function from the second law expressions, and this tells that Gibbs function at a given temperature, pressure and mass system is always less than or equal to 0. Why I say? Because when I say Gibbs function, it is measured with respect to temperature and pressure. When I say internal energy, it is measured with respect to volume and mass. Now, these two conditions imposes that at equilibrium conditions, both the parameters, a change in the parameter should be 0. So, this is the condition for chemical equilibrium, where for a chemical reactions at which the change in the entropy internal to the system should be 0, and change in the Gibbs function should be also equal to 0. Now, by putting this, let us try to analyze these reactions in the graphical form. Now, if you look at this particular figure, this is plotted against the fraction of CO2 dissociated, that is 1 minus alpha versus temperature and entropy of the mixture. What you see when you see these two graphs closely, we have some important points. First thing, that as the reaction proceeds, the entropy also of the system gradually decreases and it reaches to a maximum point and then it comes back. But we have seen that what is the extreme limit when alpha is 0 and when alpha is 1, but that is the two extreme conditions. But what we have seen is that the equilibrium temperature is reached when the entropy is maximum, because this entropy is maximum at a value of alpha is close to 0.5. So, if you drop this vertical, so you can find this number to be 0.5. So, it means not necessarily that we will have maximum entropy when the entire product is formed, and not necessarily that the reaction will proceed, or what you can say equilibrium condition is achieved only when the maximum entropy condition is reached, and corresponding to this maximum entropy conditions we can find out what is the equilibrium temperatures. So, based on this, what we can say, that composition of the system will simultaneously shift towards the point of maximum entropy when approaching either side, since entropy is a positive number or change in the entropy is positive. So, if you can just summarize what we have learnt so far about the chemical equilibriums, so you can write down like this. So, first one is the maximum entropy condition is reached, there is no further change of composition is allowed, since it requires the decrease of entropy. So, this is referred as the chemical equilibrium. In other words, the chemical reaction should proceed in the direction of increasing the entropy. Now, there are two ways to look at. One is fixed internal energy, volume and mass for an isolated system. The first law and second law and equation of state combination decides the equilibrium temperature, pressure and chemical composition. But many a times when the information about volume or mass is not known, rather we can have fixed temperature and pressure and stoichiometry, then people used to use this Gibbs function or Gibbs free energy in place of entropy. So, this entire message remains same, which says that Gibbs function always decreases for a spontaneous isothermal isobaric change of a fixed mass systems in the absence of all work effects except boundary work. So, this principle allows to calculate equilibrium composition of a mixture at a given pressure and temperatures. The Gibbs function attains a minimum value in equilibrium in contrast to entropy, which is maximum value for a fixed energy and fixed volume case. So, this is true for all chemical reactions. Now, having complete understanding of chemical equilibrium, let us see that what are the equilibrium products of combustions. So, you all know that the combustion is the result of series of complicated and rapid chemical reactions, but the formation products depends on many other factors. And this combustion product normally is determined through experimental observations by instrument like Oersted analyzer, gas chromatography, infrared analyzer and so on. So, what we want to find out from our previous study that equilibrium compositions during a combustion phenomena. So, to have this complete understanding about the equilibrium products of combustions, let us take an example, maybe one case like propane air mixture. Propane is C3H8 and it mixes with air, and the equilibrium conditions we get, or on the stoichiometric situation we get CO2 plus H2O and the nitrogen remains as it is. But what we see is the equilibrium composition, but not necessarily this composition will always come into pictures. So, we may have other components like CO2, CO, H2O, H, H2O, OH, O, all NO, N2 and N, so many atoms is there. Now, under what circumstances these species will come into pictures. So, let us understand here. We can have two situations, like the mixture can be lean or rich. Lean means it is less in fuel, more quantity of air. Rich means it is rich in fuel and less quantity of air. So, when we have lean combustions, the major product should be CO2, H2O, O2 and N2. That is quite obvious, because we do not have sufficient fuel. So, we will have oxygen as the product. Now, for rich combustion, that means fuel is quantity is more, it does not find enough oxygen. So, there cannot be oxygen at the products. So, the major product should be CO2, H2O, CO and H2 and N2. Now, what we have done is here that in a particular sample cases, people have tried to analyze and try to plot them equivalence ratio, which is a non-dimensional parameter, versus mole fraction of these reactants and products. And at the same time, let us people have find out what is the typical adiabatic flame temperature for these conditions. So, what has been observed is that with equivalence ratio, increase in the equivalence ratio, is quite obvious the adiabatic flame temperature increases and it goes to a maxima and then further drops. So, one interesting phenomena is that is quite obvious, this flame temperature increases as and when the fuel quantity is increased or the fuel becomes richer and richer, but as and when the fuel becomes rich and rich, but subsequently at one point of time fuel does not find enough oxygen. So, after this the adiabatic or maximum flame temperature drops, and the maximum temperature is observed not exactly at phi is equal to 1, rather it is at phi is equal to 1.05, and this typical number is 2278 Kelvin. So, this is the benchmark or the maximum temperature that you can achieve through propane air combustion process. And if you drop a vertical from this, then we can see what happens to other components, what happens to mole fraction of the other components. We see that the first thing, the formation of water formation, and it is again is not seen at this maximum temperature, rather it is seen when the mixture is equivalence ratio is more than 1, and whereas maximum for CO2 is observed when the mixture is lean. Of course, CO and H2O concentration increases as and when we increase this equivalence ratio, our fuel becomes rich and rich. Oxygen concentration drops, and one point of time it becomes substantially 0 because we are moving towards rich mixtures. So, all these consequences happens. So, this is what I have observed, that at equivalence ratio of 1.05 we see the maximum flame temperature, that is adiabatic flame temperatures, but the highest mole fraction is obtained at some higher equivalence ratio of 1.15. The maximum flame temperature is observed when the mixture is slightly rich. Other consequence we can draw, that for equivalence ratio between phi is equal to 1 and phi is equal to T max, the enthalpy of combustion falls more rapidly. This is one of the consequence why this maximum for the mole fraction of this is for H2O is formed at higher equivalence ratio. That is because the decrease in the heat capacity is dominated by the decrease in the number of moles of formed per mole fuel of burnt, with the decrease in the mean specific heat. And of course, when there is a dissociation, as a result of dissociation, we can see simultaneous presence of oxygen, CO, H2 at stoichiometric conditions. So, under condition of complete combustion or no dissociation, all these three species will be absent. So, this is what we see the equilibrium products of combustion for major species. Now, let us understand what are the minor species that pops in. So, minor species, as we say that in general minor species can be in the form of oxygen atom, hydrogen atom, OH, NO, all this formation can happen, and all of them are plotted with respect to mole fractions. As you see that if you drop a vertical with equivalence ratio 1, we can get many informations. With respect to this reference, first let us start one by one. The NO concentration drops when we are moving towards high equivalence ratio. OH concentration initially increases, then till equivalence ratio, and it is maxima when it is mixture is slightly lean, then it drops. The hydrogen concentration keeps on increasing. CO concentration is mostly found when the mixture is in the lean, and of course, for oxygen atom it increases, and then towards the higher equivalence ratio this number drops out, and the numbers are regarded as the minor species. And minor species means that we are looking at their numbers are not critical since they are below 4000 ppm. Of course, for nitrogen atom the concentration is several order less than the oxygen atom, and we do not find significant nitrogen. I mean, reaction is not sufficient to give species of nitrogen, but it is giving in the form of NO. So, NO formation becomes vital when the mixture is in the lean side. Okay. So, this is all about the major and minor products for during a combustion process of propane air mixture. Now, we are going to discuss a very important topic, that is called as water gas equilibriums. So, water gas equilibrium is simple chemical reactions that allows to control the composition in the products of combustion. So, how do you do that? So, normally what happens, first of all let us see what is this water shift reactions. So, water shift reaction is like we write this equation that CO plus H2O will form CO2 plus H2. So, this reaction is known as water shift reactions. So, it says that reaction can proceed in either directions. That means, CO when it mixes with water, it can produce CO2 and H2, and simultaneously they can also decompose to form CO plus H2O. So, This is called as water shift reactions. Now, why it is required in the combustion process? Now, if you look at any general hydrocarbon fuel stoichiometric combustion with air, we write CXHY, that is any fuel, plus A times O2 plus 3.76 N2 will gives X CO2 plus Y by 2O H2O plus 3.76 A N2, where A is equal to X plus Y by 4. So, this is a balanced reaction, general reaction for hydrocarbon fuel. Now, we mentioned that not necessarily always CO2 and H2O will be present. So, we can have CO2, but any general reaction can have CO2, we can have CO, we can have H2O, we can have H2, O2 or N2. So, these are the major products that can form at any instant of time. Now, the compositions like stoichiometric coefficient B, C, D, E, F, all these things are regulated by the fact that whether the mixture is rich or lean. So, basically rich mixtures will say something and lean mixture will say something. So, what does it mean? Suppose first case we say that if the mixture is lean, in lean mixture what is going to happen? The coefficient of CO and H2 will vanish. That means, the CO will vanish and H2 will vanish. So, basically the reaction for a lean combustion would be that the hydrocarbon fuel, when it reacts with oxidizer, it will produce CO2, water, O2. So, now we can have a balanced equations. So, we have components like carbon atom, hydrogen atom and oxygen atom. So, by using these equations we can find out the unknowns like B, D, F. So, these three are unknown and A is already known because A is equal to X plus Y by 4. So, A is known already. So, B, C, B, D and F are unknown, and this mass balance or atom balance can be done for carbon, hydrogen and oxygen to have a balanced equations. So, basically what it means that during a lean or stoichiometric combustions we do not require this water shift reaction because there is no CO, first thing. Second thing, or more or less we have sufficient equations to find the stoichiometric coefficients. Now, let us understand, see if the mixture is rich. When the mixture is rich, only thing that we can predict that no oxygen will appear. When the mixture is rich, there will be no oxygen, that means F will be 0, because the mixture is rich, there is no oxygen. Why mixture is rich? Because it does not find sufficient quantity of air. Then what we see? We have basically 4 unknowns, that is B, that means the reaction will have the presence of CO2, CO, H2O, H2 as well as N2, and we have all 4 unknowns, that is B, C, D, E, but the atomic balance will tell about 3 elements C, that is carbon, hydrogen and oxygen. So, we require another equations to find all the stoichiometric coefficients. This is where we realize the importance of this water shift reactions. So, if you look at this particular equations, you can see this simultaneous presence of CO and H2O in the products, and they continuously react with each other, and reaction can proceed in either side direction, and the CO can form CO, at the same time CO2 can decompose to form CO. So, there is a simultaneous process of formation of CO2, CO, H2O and H2. To have this understanding, we have to recall these water shift reactions. By doing so, what we are going to find out? We are introducing a parameter what is called as equilibrium constant, and that is defined with respect to partial pressures of each component, that is partial pressure of CO2, H2O, CO, H2O, and all these pressures are again controlled with respect to their mole fractions, and from this equation we can find Kp is equal to B times E divided by C into D. So, basically now we have three equations with respect to carbon, hydrogen and oxygen atom. Another equation will get through this equilibrium constants, which involves the Kp is equal to B times C divided by C into D. Now, if you do this, what is going to happen? That we are going to see. So, this particular thing tells about when the mixture is lean or stoichiometric, we can say that we do not require water shift reactions. The entire equations can be solved with respect to carbon, hydrogen and oxygen atom balance. So, we can find out these stoichiometric coefficients. We can also find out the mole fraction of each combustion products. But here the challenge comes when we have rich combustions. So, in the rich combustions we have basically 4 unknowns like B, C, D, E. Because F is 0, so we have 4 unknowns B, C, D, E. At the same time we have to recall the equilibrium constant Kp is equal to B times C into C into D. So, it will be a complicated equations which can be formed because this Kp is the equilibrium constant that has to be derived. So, it is a very complicated equations and all these components we can find out. But what advantage we can get is that the simultaneous control of CO2, CO, H2O and H2 can be regulated with the value Kp, and this Kp can be controlled through the partial pressures of each of these components. So, basically it is a user defined parameters which you know it earlier. By doing this, all those things can be solved simultaneously to find out the products of combustion when the mixture is rich. Now, once you know all these numbers, then it is easy to find out the composition of or mole fraction of all the combustion products. So, this is all about when the mixture is lean or rich. So, the next topic that we are going to discuss is a kind of some practical utility. So, for example, we have a rich combustions and we are unable to burn the fuel sufficiently. So, what is the next approach? So, basically the fuel has to be circulated again as a reactant. That means, the products has to be recirculated again. That is one way. Second way, we can get that whatever energy that is carried by the exhaust product, that can be tapped. So, there are two approaches for effective utilization. One is by using certain mechanical devices, we call it as recirculation or regeneration, and second concept is the exhaust gas recirculations. So, basically this is a schematic diagram of a furnace, maybe it can be a boiler or it can be any gas turbine engines, where fuel and air gets added and we get required amount of heat and the combustion product goes out, and this combustion goes out. So, instead of releasing to the atmosphere, so these products are nothing but your flue gases. When they goes out, we need to tap their heat. So, to tap that, we can use a heat exchanger, and with this perspective or application we call it as a recirculator. And what it essentially does is tap the heat from the combustion product and it is to preheat the oxidizer or preheat the air. So, this preheated air enters into the furnace. So, by this process what it does, it improves the or it enhances the adiabatic flame temperatures. So, this is one way of for effective utilization of energy. Another way of looking at this, instead of recirculator, people use regenerator. What it does it? A regenerator transfers the energy of the flue gases of incoming combustion of air. In this case, this regenerator is considered as a energy storage medium, and this storage can be in the form of a ceramic matrix, or it can be a concrete, or it can be a steel, or it can be a phase change material, it can be anything, and this stored energy is utilized whenever it is required. Either it can be used to preheat the air or it can be used for some other purposes. And whatever way, if you preheat the air, I mean it is essentially what it does is improves or increases the adiabatic flame temperature. When such a regenerator or recuperator is used, we can use this lean mixture, because when you are using during lean combustions, we means that we have burned the fuel sufficiently, but the exhaust product has sufficient heat. So, in that such situations, the regeneration recuperation can be used, concept can be used to tap the heat. But in other scenario, when you have a rich mixtures, that means we have not extracted the fuel energy completely. So, that means the mixture is again still have some capability to initiate the reactions. So, during that conditions, we use the concept called recirculations, and we call this as a fuel flue gas recirculations. So, recirculation means like whatever exhaust product that comes, it is before it is being fed out, some part of these things is again fed into this system or the reactor. So, through this process, what we are going to get is that we can tap this heat. At the same time, whatever unburnt fuel is there, they can be recirculated with the fresh charge, and as a result you can get an effective combustion. One advantage of this is that we can lower the NOx formations. That is the essential advantage of this recirculations. So, there are two concepts associated with it. One is flue gas recirculations, which are very common techniques when people use for boilers or furnace. Now, when you are doing research in IC engine, people used to take some part of exhaust gas and recirculate it, and that they mix with the fresh air, and such a concept we call it as a exhaust gas recirculation, and that is very common in the automotive engines. Now, with this I close this module, but before you complete this lecture, let us understand some of the basic problems which you have covered in this class. So, again this we can say one particular problem which we typically use mainly while calculating the flow rate, mass flow rate and air fuel mixture apart from the conventional fuel. Conventional fuel are normally petrol or diesels, but many times we use some composition of fuel, like this is a one fuel where which is closely resembles to natural gas, that is C 1.16 H 4.32. So, this is another hydrocarbon fuel one can think of while using in any kind of gas turbine engines. So, what is given, and basically what we are trying to say is that again we are revisiting to calculate the air fuel ratio, fuel air ratio, mass flow rate, all these fundamental concepts. So, the problem that is given to us, that we are known with the equivalence ratio which is 0.3, we are known with the air flow rate, that is 950 kg per minute, we have given with the composition of the fuel, and we need to calculate the mass flow rate of the fuel and equivalence ratio. So, to start the solutions, what is given is phi is 0.3 and m dot A is 950 kg per minute, and that can be calculated as 15.8 kg per second. Okay. And what we need to find out, what is m dot F and what is A by F, air fuel ratio. These two numbers we need to calculate, and before you do that we need to recall what is mass or molecular weight of the fuel, and from this equation we can find out this number will be 12 for carbon molecular weight into its 1.16 plus hydrogen molecular weight 1 into 4.32, and this number is 18.24, and for molecular weight of air we know is 28.97. So, these two numbers we know. Then we have to write down the equations, like if you say general equations Cx Hy plus A times O2 plus 3.76 N2 this will give you x CO2 plus y by 2 H2O plus 3.76 A N2, where from these equations we can find out A is equal to x plus pi by 4. Now, if you apply these particular equations here, x is equal to 1.16, y is equal to 4.32. So, this will tell you what is the value of A. So, A will be 2.24. But now, we are in a position to calculate what is air fuel ratio for the stoichiometrics. So, A by F stoichiometric fuel ratio can be found out, that is mass of air by mass flow rate of fuel, and this is nothing but in terms of molecular weight 4.76 A divided by 1 into its molecular weight. Molecular weight of air is Ma by Mf. So, we all know this number, but we have A, we have Ma, we have Mf. So, we can find out air fuel ratio stoichiometric value will be 16.92, and we know phi, that is A by F stoichiometric by A by F, and this will give you A by F is equal to, actual A by F will be, because we have phi is 0.3. So, actual A by F would be 16.92 divided by 0.3, that is, that number is 56.4. But what we require again, the mass flow rate of the fuel. So, that is m dot A by m dot F is equal to 56.4. So, this will tell you what is m dot F, because m dot A is known 950 kg per minute. So, m dot F would be 15.8 divided by 56.4. So, m dot F is equal to 0.28 kg per second. So, this system requires 0.28 kg per second of fuel, while air quantity is 15.8 kg per second. Then moving further, there is another problem which says that natural gas fired industrial boiler, it operates with oxygen concentration 4 mole percentage of flue gases. Now, let us see what is this mean by flue gases. Normally, for hydrocarbon fuels, when they burn, they produce CO2, H2O, O2, N2. So, these are called as flue gases. So, you should understand the term like flue gases. So, you can assume that normally when you say natural gas, its main compositions one can blindly assume it is CH4. So, you can say it is a methane air combustion. So, you can write this equation as CH4 plus A times O2 plus 3.76 N2, it gives CO2 plus twice H2O plus B O2 plus 3.76 A N2, and these are nothing but your flue gases. And in these flue gases, it contains 4 moles percent of oxygen, only 4% of oxygen. Okay. So, if you make this oxygen atom balance, one can write 2A is equal to 2 plus 2 plus twice B. So, this means B is equal to A minus 2. So, one equation we get it. Other equation we can say x of O2 is equal to 0.04, and what is this x of O2? That means number of moles of L2 divided by total number of moles in the mixture. and number of moles of A2 is B divided by number of moles in the mixture will be 1 mole here, 2 mole here, B and 3.76 A. So, 1 plus 2 plus B plus 3.76 A, and that number is equal to 0.04, and this will give you an expression B is equal to 0.12 plus 0.04 B plus 0.1504 A. So, we have two equations, one is this, another is this, and unknowns are A and B. So, after solving, we can get A is equal to 2.52 and B is equal to 0.52. Now, with this number we are now able to find out what should be the air fuel ratio. So, air fuel ratio would be number of moles of air by number of moles of fuel into molecular weight of air by molecular weight of fuel. So, this number would be in this case 2.52 into 4.76 total number of air into A. Molecular weight of air is 28.97 divided by fuel is 1 mole into 16 is the molecular weight of methane. So, this number is 21.72. Now, when I say A by F stoichiometric, at the stoichiometric you have A is equal to x plus y by 4. So, x plus y by 4 means that is 1 plus 4 by 4 for methane. For methane we can write x is equal to 1, y is equal to 4. So, A is equal to 2. So, number of moles will be 2 into 4.76 into 28.97 divided by 1 into number of moles of fuel is 1 into 16. So, this number is 17.23. So, we have air fuel ratio 21.72 and equivalence ratio 5 will be A by F stoichiometry divided by A by F actual, and in this case it is 17.23 divided by 21.72. This number is 0.79. Okay. So, this is all about the type of fuel that we are using and how their compositions are going to affect the equilibrium products of combustion. So, with this I conclude. Thank you for your attention.